Okay, I want to thank the organizers for giving me an opportunity to speak here. So I'm going to be talking about p-adic Asai transfer. All this is joint work with Dipramit Majumdar. Okay, so let me just sort of recall what the Asai transfer is. You've already sort of seen the Asai L function yesterday, but I'm going to be working in a slightly different situation. So let F be a real quadratic field. So this is as opposed to imaginary quadratic field, which was what we were looking at yesterday. And suppose F is a Hilbert modular form over capital F of let's say weight K and level 1. So I mean, this is just sort of just to introduce. I mean, we don't really need this assumption later on. Then Asai in a paper in 1977 introduced this function, which is now called the Asai function. So this is given by sort of the same formula that we had yesterday. So it's essentially you take this kind of a Dirichlet series, sum m equals 1 to infinity. You take the Fourier coefficients of this modular form, the Hilbert modular form, at ideals coming from Q. So divided by m to the power s. But then this doesn't have a nice Euler product formula, so you sort of need to fudge this by zeta term. So you need to multiply this by zeta of 2s1, where s1 is equal to s minus k plus 1. So then in this paper, so as I studied sort of the analytic properties of this L function, So in particular, this L function has an analytic continuation. It has an Euler product formula and functional equation. Yeah, and the Euler product. So this is sort of a degree 4 L function, by the way. So by what I mean by this is that in the Euler product, so you usually have 1 over some polynomial evaluated at p to the power minus s, and this polynomial has degree 4 basically almost everywhere. So this is sort of what Asai did in his 77 paper. This actually now also has, by the way, there are, I mean, you can sort of generalize this. So here I just sort of gave the formula for, level 1 and so on. But then if you have arbitrary level, or if you have some Nebentapers, you have to sort of modify this by replacing the Riemann zeta function by Dirichlet L function. But so that's not too difficult. So this has a description in terms of Langlands functoriality. Yeah, so basically I'm starting with sort of a modular form over GL2, modular form for GL2 over F, and I'm ending up with an Euler, like an L function which has a degree 4 L function, and in this case it turns out to be associated to something coming from GL4. So the two groups that we are interested in are G1, which is restriction of scalars from F to Q, of GL2 over F, and G2, which is just GL4 over Q. Now the Langlands group, the Langlands dual for G1 is, you can actually just write this as GL2C cross GL2C, semi-direct product Z mod 2Z, where Z mod 2Z is actually the Galois group of F over Q, and the non-trivial element here acts by just permuting these two elements. And then the Langlands dual for GL4 is just GL4 over C. And then, so we want to sort of now give a map at the level of these L groups. So the maps are, which I'm calling Asai plus minus. Again, as Eknath said yesterday, there are two transfers. One is the Asai plus and the other is the Asai minus. So this is going to be a map from GL, so G1L to G2L, and what is this given by? So I'm actually just going to write this as GL of C2 tensor C2, and then so the Asai plus minus of an element in here, if I have a tensor B, this acts on X tensor Y as just AX tensor BY. And then the Psi plus minus on the non-trivial element over here is given by, its action on X tensor Y is just plus or minus Y tensor X. So this is essentially just the sort of the tensor product of these two matrices. But then the complex conjugation, not the complex conjugation, but the non-trivial element in here, it acts by sort of flipping these two vectors and adding a plus or minus sign depending on whether you are in the Asai plus situation or the Asai minus situation. Yeah, A comma B. Sure. Yeah. All right. So this gives us a map between L groups, and then the principle of Langlands functoriality says that there should exist an automorphic representation, so like capital Pi of GL4 over the adales, such that the L function of this L as capital Pi is actually equal to the Langlands L function of little pi with respect to this this representation. So here little pi is actually an automorphic representation of G1. So basically, this capital Pi is what we call the Asai plus or minus transfer. So actually, I should really have two. So this capital Pi is denoted by Asai plus minus of pi, of little pi. So from now on, we want to use capital Pi. Okay, so. So we have this, so in particular, okay, so how do I connect it to this, so this sort of classical L function? If I start with, so if I take pi to be an automorphic representation which is associated to Hilbert modular form, then the Asai plus minus L function, in fact the Asai plus L function will turn out to be essentially this L function up to a shift. I mean, always when you go from classical to automorphic, there's often a shift. So there's a shift in this case. And then the Asai minus is sort of the twisted Asai function that Eknath was talking about. Sorry.
So you have two as plus minus.
Yeah.
Oh, okay. So the other one is as plus minus of pi. It has nothing to do with the earlier as plus minus.
So I'm just calling it as as plus minus of pi. That's it. I mean, it's just a notation.
But your earlier as plus minus is this morphism.
Yeah, so if I took as plus, then the corresponding representation, I would call it as plus of pi. If I took as minus, then I would call that as minus of pi. That's it. It's just a notation, like the...
Independently, what is the right hand side? You have your as plus minus.
Yeah.
Of course, you don't have your capital pi.
So the capital pi comes from this L function, which comes from this representation.
Okay, so the right hand side is an L function associated to that automorphic representation.
Yeah. So if I have little pi, I mean this is just the Langlands L function associated to little pi with respect to this representation, and the left hand side is the standard L function for GL4 object. Yeah, no, it is known. So it's yeah. So the existence, I was just going to say that the existence of Dinakar and Muthu Krishnamurty, independently they proved that it exists. So by the work of Dinakar Ramakrishnan and Muthu Krishnamurty. So this is around 2002 or 2003. Showed the existence of this Asai plus minus of pi. Okay, so this is sort of the Langlands functoriality that we are interested in. So this is sort of the starting point. Now, in some sense, like one of the natural questions is suppose you take let's say two small pi's which are p-adically close, then can you say that the Langlands transfer of those two are p-adically close? So this is sort of the question that we want to try and answer. So if pi and pi prime are p-adically close, so then are the Asai transfers of pi and pi prime p-adically close. So again, I have to sort of make sense of what p-adically close means. So here again, like there are sort of different notions of what it means to be p-adically close. So here I'm going to take p-adically closed means that p-adically close means they're means that they're close on the eigenvariety, on an appropriate eigenvariety. So will mean they're close, again within quotes, on an eigenvariety. So let me sort of give a quick introduction to eigenvarieties. No, I'm fixing a p now. Yeah, of course. No. Yeah, you can construct that. I mean, yeah, there is. So exactly, yeah. So again, the Satake parameters, you can actually write it down in terms of the Fourier coefficients, sort of the roots of the Hecke polynomial. That will take care of almost all the primes.
Mm-hmm. And every homomorphism of every you can attach like an L function, but you don't know whether it's coming from an
yeah, exactly.
Transfer itself.
Yeah, so you don't know whether it's actually coming from an automorphic representation or whether it's just a L function. So yeah, so all those things will come. Yeah, so we have to, of course, when we talk about eigenvarieties, you have to assume that they're finite slope. All right. So let me maybe give sort of a quick introduction to eigenvariety. So eigenvariety is basically a rigid analytic space which parameterizes, often parameterizes like p-adic automorphic forms or like over-convergent p-adic automorphic forms with respect to a certain group. So, so usually eigenvariety is constructed using what is called Buzzard's eigenvariety machinery, which sort of starts with an eigenvariety datum. So datum and sort of outputs an eigenvariety. So let me just sort of explain what goes into this. So what goes into this eigenvariety datum? So an eigenvariety datum is actually of the form. So there are. So I'll just explain what these are. So there's a space W, Z, and a sheaf M, an algebra T, and psi. So this is what is called an eigenvariety datum. So here W is what is called the weight space. So this is a space which parameterizes all so all your classical and also p-adic weights. And Z is so what is called a spectral variety. So spectral variety. So this is actually a sub domain of, no, not a domain, it's a closed subvariety of the weight space cross the rigid analytic affine line. And sorry? Yes, yeah. So it's a rigid analytic space that parameterizes p-adic weights. And spectral variety is basically it's constructed by basically patching together various freedom hypersurfaces, and it has the property that so Z is parameterized by the following property. So if you have some kappa, comma alpha inverse belonging to Z, then there exists, or rather the space of overconvergent automorphic forms of weight kappa and slope alpha is non-zero. Yeah, and since I'm actually taking alpha to be non-zero, this parameter is as finite slope over convergent automorphic forms. So again, so right now, okay, so this I have to put it in a bracket because right now this is just an abstract space. But when this is an eigenvariety datum associated to a group, then this would be automorphic forms on that group. Okay. And then M is a coherent sheaf and this is usually like it's a coherent sheaf of overconvergent automorphic forms. T is a QP algebra. Sorry, what? Yeah. So I have to make sense of all those things. So those will come later. So this is just sort of what will Z eventually be. Okay. So this is a QP algebra, which is the Hecke algebra. And and psi is so psi is actually a map. I mean, it's actually the action of the Hecke algebra on the sheaf. So the sheaf of overconvergent automorphic forms comes equipped with a Hecke action, and that's denoted by psi. All right. So given this ingredients, sort of purely abstractly, Buzzard constructed an eigenvariety so an eigenvariety which is called x of d usually associated to this data. So basically this is again a rigid analytic space which is finite over Z, which is spectral variety, but then Z is actually a subspace of the weight space times the rigid analytic affine plane. So there's a projection map from Z to W. So you actually have a map from X to the weight space. So you think of it as a rigid analytic space over the weight space. And this is actually parameterized by sort of the following property. If you take Z in your spectral variety, then the points in X above, so basically the fiber of Z are actually they correspond to generalized eigenspaces for the action of T on the stalk of M at Z. So this is stalk. So M of Z basically sort of corresponds to overconvergent modular forms of weight kappa and slope alpha. So that's how you parameterize this space. And so the points on the eigenvariety basically just correspond to generalized eigenspaces of this Hecke action. And then, but then you know that you can actually relate that to sort of automorphic forms and Hecke action on automorphic forms. Okay. So what? This is sort of the next question so this is sort of Buzzard's generalized construction. So the next question that one wants to ask is, so suppose you're given a reductive algebraic group G, then how can you sort of construct an eigenvariety associated to G? So which parameterizes over-convergent automorphic forms on G. And so essentially it's nowadays it's actually constructed using this machinery. So given a G, you have to sort of come up with appropriate, with an appropriate eigenvariety datum. Most of these things are fairly obvious. The weight space is obvious. The Hecke algebra is also more or less obvious. And then Z kind of depends on your space of over-convergent automorphic forms, and M also depends on your space of over-convergent automorphic form. So sort of the most difficult step in this process is actually constructing this sheaf M. So constructing an appropriate space of over-convergent automorphic forms is actually what is most difficult. And so classically, this was, for example, done first by Stevens, who constructed like the eigen curve using this approach by using over-convergent modular symbols. So that's his thing, and this Buzzard's construction basically just formalizes this whole process. So there are sort of two groups involved in our picture. One is the restriction of scalars from GL2 over F and GL4. So these are the two groups. So now the question is, what will we take our eigenvariety to be? And this is a construction which was done a couple of years back by Hansen. So So there are sort of various steps starting. I mean, this Buzzard's paper is from 2006, and then in basically the last 10 years, there have been sort of various progressions. So now I'm just going to sort of state like the final form of this, which is due to Hansen, but it builds on the work of Urban and maybe Andrietta, Ioveta, Piloni, and sort of many others. So Hansen constructs. Also Emerton, I should mention Emerton, constructs the eigenvariety associated to a general reductive group, to G, by taking your over-convergent modular symbols to be basically, sorry, so the sheaf by constructing M. So I'll just say that by constructing M out of complexes, of augmented Borel-Serve complexes. So this is sort of a fairly technical construction, so I won't go into it. But so the cohomology of this complex is actually so you actually get sort of so the cohomology of a certain open compact subgroup. So let me call this K. So with coefficients in a certain sheaf, in a certain vector space or a module of distributions. So this is the same distributions which appeared in Shanlon's talk, something similar actually. Yesterday. So here, what is K? So K is actually an open compact inside G of the finite adels. And then this has, so K actually breaks up as sort of a tame level. So this is away from P. And at P, you have to usually take Iwahori level. This is actually something similar to what is done in Hida theory. For example, when you look at Hida families, you have to consider sort of you have a tame level and then you have a level at P which is always divisible by P. Okay. Sorry? Oh, sorry, by constructing M. So the sheaf M is actually constructed out of certain complexes whose cohomology is this. So since this cohomology plays a role, so you can't actually, for example, get all over-convergent automorphic forms. You only get automorphic forms which contribute to cohomology. So I don't want to sort of go into that, but for example, you won't get something like Mars forms out of this, because Mars forms won't contribute to cohomology, but you would get modular your classical, so the holomorphic modular forms and Hilbert modular forms, because they contribute to cohomology. Okay. So this is sort of the first step. So once you construct this, you actually also want to be able to construct maps between eigenvarieties. And this is also done by Hansen, which is generalization of work of Chenevier. So again, so this is called comparison theorem usually. So generalization of work of Chenevier. So this actually allows you to construct maps between eigenvarieties. So let di be two eigenvariety data. Then, so what does the comparison theorem say? It says that suppose you have a closed immersion J from the weight spaces so the weight space of W1 to the weight space W2. Second, you have a map homomorphism sigma from between the Hecke algebras. So this is in the opposite direction. So you have a map from T2 to T1. And third, so a Zariski accumulation dense subset. I mean, so Zariski accumulation dense is like sort of a stronger version of Zariski dense, but dense subset of the spectral variety so Zariski accumulation subset Z1. So these are usually called classical points sitting inside Z1 and an extension of J to these classical points such that if I look at the stalk at Z, there's an inclusion of the stalk into the stalk of Jz, or rather after semi-simplification. So you have an inclusion, so that there exists an inclusion which is T2 Hecke equivariant. Sorry? What order? So which is T2 equivariant. So you want actually an embedding of this stalks, or the semi-simplification of the stalks from Z to Jz, which is equivariant with respect to T2. So here, this side, obviously there's an action of T2 because Sorry, I should say M1, M2. So here obviously there's an action of T2, but then on this space there's an action of T1, but then you use sigma to extend, to pull back this action to T2. Sorry? So there is no Z, yeah, in fact it should, that's sort of the whole point. Just one second. So this Z1 classical will actually be sort of a space above so-called classical weights, and this will parameterize classical automorphic forms. And then in all our applications, what we want is we are trying to interpolate some kind of a classical transfer. So this classical automorphic forms will go to some classical object on the other side, and you want to sort of extend this to p-adic automorphic forms as well. So that's what we are trying to do. Yeah? Okay. So if you are in this situation, then there exists a rigid analytic map from x1 to x2. By the way, I did not sort of state this theorem correctly. So in fact, there are some technical conditions. So in fact, you cannot construct this map on the whole of x1. In general, what you can do is you can only construct it on a closed subvariety of this. But in our application, that closed subvariety is actually going to be the whole of x1. So I'm not going to say much about it. So the thing is that if your group does not have discrete series at infinity, then you cannot actually construct this map on the whole of x1, but you can actually only construct it on a closed subvariety of x1. And in our case, we are actually, this is going to be the eigenvariety associated to GL2 or F, which has discrete series, so we are fine. I don't have to have, so the GL, on this side, I'll have the eigenvariety associated to GL4, which does not have discrete series, but that is not an abstraction. So I only have to have discrete series on the left. Okay. So let me now sort of become a little bit more specific. So for example, if I start with a group G, what is the weight space, what is the Hecke algebra, and so on. So I'm actually just going to do this in the specific case that we are interested in. So that sort of maybe will give you a general idea. So first, let me take G to be G1, which is restriction of scalars from F to Q of GL2 or F. So in this case, the weight space is a rigid analytic space whose QP points or QP bar points are given by continuous homomorphisms from the torus. So this is the maximal torus of G from the torus to I guess QP bar. Yeah. So this is sort of your big weight space, but then when you introduce, so you also have to sort of introduce some level structure to this. So there is an additional condition, and the additional condition is that this actually factors through so this factors through so that that factor through the center, the points of the center in KPI intersection GQ. So the GQ sort of sits diagonally inside the finite ideal, so I can actually view this as a subset of TQP. So here Z is the center, and actually I just take the closure of this. Okay, so this is sort of equivalent to, for example, in Hilbert modular forms, you have this condition that there's some parity condition, so it's sort of equivalent to that. So in this case, it's going to be a restriction, right? So it's going to be like a product of two torus. So I mean, so it's a restriction of the maximal torus. Yeah. So here I'm just going to take the restriction of the split torus from GL2. So that's kind of the standard one that one takes. Okay. So I'm in fact like so for example now I assume that P splits in F. So then I can actually just identify TQP with T of so let's say P is equal to P times P conjugate. So this is actually just T of FP cross T of FPC. So which means that this is a four-dimensional space, right? I mean, like I have, each of them have two variables, so I have four variables, and I'm modding out by something here, and this is a one-dimensional space. So the eventual this thing is going to be three-dimensional space, so three-dimensional analytic space. Okay. Now, on the other hand, the weight space for so the weight space for G2 which is GL4 is also defined similarly. So instead of the torus of GL2, I'll have to take the torus of GL4. So which means I'll get a four-dimensional space. But then since I'm actually only interested in automorphic forms of that contribute to cohomology, there is this Clausel's purity condition on the weights, which will sort of cut down one dimension. So I'll actually eventually just get three dimension on this side as well. But I don't sort of need it at the moment. Okay, so we need to now construct a map between these weight spaces. So that's the first step in, right? I mean, this map J was from the weights, it was a closed immersion on the weight spaces. So, let me just quickly say how to do that. So if I have, so I want to construct a map like this. Now, what is the weight here? So here I'm actually just going to sort of think of this as weights of Hilbert modular forms. So an element here is actually of the form n comma v, where n is equal to n1 comma n2, and v is equal to n2 comma v2. And then this condition basically says that n plus 2v is parallel. So this is some m comma m. Okay. Since so Hilbert, I'm working with Hilbert modular forms over quadratic extension. So weight is sort of a tuple of integers, one for each embedding. Okay. And now, so suppose kappa is this weight, then what is kappa going to map to? You can actually check that kappa will map to, sorry, where is this? Sorry? So here I'm thinking of N1 and N2, so I'll just identify one on each torus. So, or rather, okay, so let me be precise. So the association is, so I'll send this weight to the weight N1 plus V1, comma V1, comma N2 plus V2, comma V2, right? Like where N1 plus V1 over V1, this is going to give me a weight here, and then N2 plus V2, comma V2 is going to be giving me a weight here. So that's the translation which preserves. So you want also to sort of preserve this highest weight module, right? I mean, like, so there's a highest weight module associated here, and then there is also this space of polynomials of degree n on which there's an action of GL2, right? I mean, that's so in this situation, so you want them to match, and then this is the identification that will make these two spaces the same. Okay. Yeah, sorry. So then this weight goes to the following weight for GL4. This is actually given by N1 plus N2 divided by 2 plus M minus 1. So maybe I should actually, I need more space for this. So kappa goes to N1 plus N2 divided by 2 plus M minus 1, comma N1 minus N2 divided by 2 plus M minus 1 plus M minus N1 minus N2 divided by 2 and M minus N1 plus N2 divided by 2. So, so this is sort of going to be the weight map. So I send a weight W1 to this weight W2. And then one thing that you have to notice here is that if N1 is actually equal to N2, then this is actually going to cause a problem because this would be 0. And then in that case, this weight actually you can show will not support cohomology. So you cannot actually allow N1 to be equal to N2. So if N1 is equal to N2, then this weight will not have any homological automorphic forms. So you want to actually sort of restrict, so you actually don't want to allow this condition. And then just for the sake of continuity, you actually just assume that N1 is actually bigger than N2. So that's, yeah, so parallel weight, the Asai transfer is not cohomological in GL4, so you cannot do that. All right, so this is the map at the level of weight spaces. So let me now explain the map at the level of Hecke algebras. So you want a map. So first, okay, let me sort of say what the Hecke algebras are going to look like. So the Hecke algebra T1 is actually going to it's going to actually have a component at P, and then sort of a component away from P. So here I'm actually just going to take my tape level to be maximal compact. So which means it's like the sort of your usual sort of Hecke algebra at sort of primes not dividing the level. So this is generated by sort of T, Q, S, Q as Q varies over primes in F. And just for sort of simplicity, I'm actually just from both sides, I'm actually going to throw away ramified primes. So Q unramified in F. Throwing away finitely many is fine because of multiplicity 1, it's not going to affect any of our calculation. So now this is actually going to be a certain subalgebra inside, so this is actually going to contain sort of your UP operator and UPC operator and also the SP operator and SPC operators. And these are your operators, and then you actually also invert these operators. So once you invert them, you get a slightly bigger algebra, which is called A1P without the plus. And this sits inside your Ivohori Hecke algebra. So because the Ivohori Hecke algebra is not commutative, so and you want something commutative, so you actually take sort of this smaller one. All right. And then the Hecke algebra on the GL4 side is actually again going to look like you'll have a part supported at P, and then so this is away the part away from P. Again, I'm going to take my tame level to be maximal compact, so I'll just take it to be GL4 of ZP. ZL4 of ZQ for all Q not equal to P. And again, I throw away the primes which are ramified in F. So this will actually is generated by sort of 4 Hecke operators at each prime. So we just call this TQ1, TQ2, TQ3, and TQ4. And then here, again, so by the way, this is over F, so which is why you have, so you have primes over F, but this is over Q, so all the primes here are just over Q. And you have, corresponding to these UP operators, you have UP1, UP2, UP3, UP4. So these are sort of the 4 operators. And so then we are actually just going to use the comparison theorem to construct this map between the eigenvarieties. And we know that in order for so one of the conditions of the comparison theorem is that this map sigma should be defined from T2 to T1 such that this inclusion is Hecke equivariant and this kind of fixes our map sigma for us, because if you start with Sadeke parameters for your Hilbert modular form, then you have an explicit description of the Sadeke parameters for the Asai transfer. So using that, you can actually just compute this map sigma. So I'm actually just going to write down the final result. So sigma plus minus is given by the following. Yeah. 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 So that will sort of force sigma for you. I mean, like, because you know the Satake parameters for the Asai transfer. So which means you know the Hecke polynomial, which means you know what the Ti operators will act by. So so this sigma plus minus is actually just given by, so I have two cases. So well, I have three cases when Q not equal to P and Q is equal to QC. So in this case, I have to send TQ1 to TQC, TQ2 to Q square SQC plus SQ TQC square minus to Q SQC. And then TQ3 has to go to Q inverse TQ SQ TQC SQC, and TQ4 goes to Q to the power minus 2 SQ square SQC square. And then Q not equal to P, Q inert. So in this case, TQ1, by the way, so this one actually doesn't depend on whether you're using Asai plus or the Asai minus transfer, but then this second one will. This is plus minus TQ, TQ2 goes to 0, TQ3 goes to minus plus Q inverse TQSQ, and then TQ4 goes to Q to the power minus 2 SQ square. So finally, let me just write what the UP operators will do. So UP1 will go to UPC, UP2 goes to UP square SP, and then UP3 goes to inverse UPSP, UPC, SPC, and UP4 goes to P to the power minus 2 SP, SPC. So this is sort of the explicit map at the level of Hecke operators, and then this, along with that weight map that I wrote down earlier, will actually satisfy all the hypotheses of the comparison theorem, so which will actually allow us to construct a map between eigenvarieties, and then this eigenvariety at classical points will send your classical automorphic forms to the Asai plus or minus transfer of this point. So this is a p-adic extension. So here I just one more point. I assumed that P splits because there is actually one problem when you assume P is inert. When P is inert, it turns out that everything else I can do except that I don't have a candidate to send UP2 to. So there's nothing on the other side where UP2 should go to, but there's an obvious choice for UP2 square. So you don't actually get a map to the eigenvariety of GL4, but you get a map to the eigenvariety of a quotient of GL4. So in that case, this eigenvariety only it parameterizes automorphic forms, but it cannot distinguish. I mean, it only distinguish. It can only recognize UP2 square. It cannot recognize UP actually. It's a quotient of the GL4 eigenvariety. I'll stop. Yeah, so the reason is because so it's a by hand construction, but the reason we get this is because we know the Satake parameters for the Asai transfer. So you just plug it in. So and the Satake parameters have to be the roots of the Hecke polynomial. So it's actually just you just write it down. You compare both sides of the Hecke polynomial, and you get it. So that's it. Sorry?
I mean, your result is that if something is periodically closed, then
on the other side, no. So it's not like, so if you give epsilon, I cannot find delta. Yeah. So this in fact gives. So if you start with a Hida family. Passing through Hilbert modular form, and this works for finite slopes, so ordinary is finite slope. In fact, it's more general. Like even for Coleman families, it will work. So if you take a Coleman family passing through a Hilbert modular form, then the Asai transfer of that is also in some sense a family. So yeah, I sort of swept that under the carpet. So the thing is that in this eigenvariety, there's something called a refinement. So you have to choose a specific ordering of slopes. So on both sides, you actually choose a specific ordering of slopes. So for example, here I choose like alpha p, beta p, alpha p, p bar, beta p bar. So for that particular ordering, I get a particular ordering of slopes on the other side. So it's so this map depends on a certain ordering of slopes. So if you change the ordering, you'll get a completely different map between the eigenvarieties. In fact, the eigenvarieties themselves will be.
Formulas for those slopes.
Yeah.